Lecture 33 is the second lecture on dielectric properties of materials. In this lecture, we talk about the 4 different kinds of polarization mechanisms. We talk about the frequency response using the Lorentz oscillator model and using the relaxation model. So the first student learning outcome in this lecture is that you should be able to identify the 4 different polarization mechanisms in given materials. We have electronic, ionic, dipolar or orientational, and interfacial polarization. So obviously, the electronic polarization occurs in every type of material because we have atoms everywhere. And the polarizability does depend on the strength of electron binding to the nuclei. The polarizability will be higher for valence electrons than for the core electrons. And as you move down the periodic table in the same group, atoms become bigger. So you should expect to see larger polarizability. Now, in ionic systems, we have ion pairs, and the positive and negative ions will be displaced in opposite directions if we apply electric field that generate a net dipole moment per ion pair. So that's the so-called ionic polarization. In systems where we have dipolar molecules with the permanent dipole moment, these dipole moments will be partially aligned with the electric field. The different alignment of the dipole moment will generate different potential energies. That potential energy causes the preferential alignment of the dipoles in the direction of the electric field. But on the other hand, we do have thermal agitation. We have thermal energy, which tends to randomize the dipole moment. So it's a competition between the actual potential energy caused by the electric field, and we have the thermal energy. Finally, we may have interfacial charges somewhere that also can the movement of those charges can also create a so-called interfacial polarization. The second student learning outcome is that you should be able to calculate the dielectric constant based on what's there. What are the contributing polarization mechanisms in a specific material? So we say that for the electronic and ionic polarization, as we talked about in the last lecture, you want to apply the Clausius-Masardi equation to relate the microscopic polarizability to the macroscopic dielectric constant. And for dipolar and interfacial polarization, you just simply use the simple form of dielectric constant in this simple form. So in this case, it is important that you identify what's there, and then if there are multiple polarization mechanisms, you need to sum up all their contributions. But understand that in different materials, we have different polarization mechanism contributing, but at the same time, it also depends on what kind of frequencies we're looking at. Different polarization mechanisms have different frequency response. This is related to the next 2 student learning outcomes. So we have 2 different models. One is called a Lorentz oscillator model. The other is a relaxation model. So you should be able to know the general form, general characteristics of those 2 models in terms of what they predict the frequency response for the dielectric constant, and then also interpret the physical meaning of the real and imaginary parts of the dielectric constant. Finally, you should be able to compare the characteristic frequencies of the 4 polarization mechanisms, put them on the same plot and see how they behave. So for the Lorentz oscillator model, the polarizability can be written in this form. Omega 0 is so-called resonant frequency of these oscillators. And understand that we have both the real part and imaginary parts for the polarizability. And since we have a relationship between the dielectric constant with the polarizability in this simple form, they are sort of linear they have a linear response, linear dependence. So that also means that we're not going to see the real and imaginary parts in the dielectric constant as well. And obviously, the imaginary part will be directly proportional to each other, and the real part will have a linear dependence in between them. So if you plot out this frequency response of this Lorentz oscillator model, looking at the polarizability scale to the polarizability at 0 frequency, you're going to see this general form. Looking at the imaginary part, you will see a peak centered around the resonant frequency, and away from this is the resonance. Off resonance, you are going to see the imaginary part die down almost to 0 when you go very far away, either in very low frequency or very high frequency. That also means that the imaginary part of the dielectric constant will have the same behavior. We have a resonance at the resonant frequency, and then going away, you have either 0 frequency or high frequency. You're going to see the imaginary part of the dielectric constant going to 0. For the real part, it'll go through a positive maximum to negative maximum transition at around the oscillation, the resonant frequency. And then going to low frequency, the real part of the polarizability will go to some final value that gives you a dielectric constant greater than 1. Going to high frequency, the imaginary part, the real part of the polarizability will go to 0. That gives you a dielectric constant of 1 at high frequency. This is the Lorentz oscillator model. It's a classical model. Then we also have the relaxation model. This can be applied for dipolar or interfacial polarization. The Lorentz oscillator model applies to electronic and ionic polarization. For the relaxation model, the polarizability has such a frequency response. Tau is the so-called relaxation time. And so when you look at the overall response of the dielectric constant goes through a high to low transition around 1 over tau for the angular frequency. And for the imaginary part, it also has a peak, sort of similar to the resonant peak for the Lorentz oscillator model, but the frequency for that peak corresponds to 1 over tau for the angular frequency. Again, going away from that frequency, you see the imaginary part goes to 0 on either end. So this is the general behavior of the relaxation model. So when you combine all those models and then looking at the 4 different kind of polarization mechanisms, you can have the overall frequency response as shown here. First of all, we use the classical Lorentz model. We can use the classical Lorentz oscillator model to describe the dielectric response for the ionic and electronic polarization. Obviously, in this case, you see that you have resonant peaks for both the ionic and electronic polarization, but understand that these resonant frequencies are different. In the ionic situation, the ions are oscillating. In the electronic polarization, the electrons are oscillating. So obviously, electrons have much smaller mass than the ions, so their oscillation frequency will be a lot higher. So typically, for the electronic polarization, the resonant peak occurs typically in the visible to ultraviolet spectrum region, and for ionic oscillation, the resonant peak happens typically in the infrared, about 2 orders of magnitude low, 2 to 3 orders of magnitude lower in frequency. But obviously, the classical model only applies in. I mean, you can use them in sort of a certain way to describe the general behavior, but the specific line shapes actually will be different if you use a quantum mechanical model. On the other hand, for the orientational dipole or the interfacial charges, we can apply the relaxation model that gives you a sort of high to low change for the dielectric constant, the real part. And the imaginary part will also show up at peaks, but that peak happens at 1 over tau for the angular frequency. And the orientational dipole typically will occur in sort of a radio frequency region, and for the interfacial dipoles, it'll typically occur at much lower frequency, maybe like 1 hertz or even lower, depending on what kind of charges that are involved in these polarization mechanisms. So overall, now we can look at the meanings of the real and imaginary parts of the dielectric constant. The real part is really the ability of the medium to counteract the external applied electric field, because we have the depolarizing field, and then the depolarizing field scales with the electron susceptibility. So that means that if for a material that has larger dielectric constant, the depolarizing field will be stronger, so it can be more effectively screen the external field. On the other hand, for the imaginary part, it's really representing so-called dielectric loss. That is, we have a sort of resonant. Whereas a resonant of the atoms or electrons in the system. So obviously, when we have a larger imaginary part, that means the oscillation of these electrons or ions will be bigger. So that means we have high internal energy. The energy comes from the oscillating electric field on the outside. So that means we have a stronger coupling between the external field and the internal energy. So that means that we have, when the material has a higher imaginary part of the dielectric constant, they can more easily obtain energy from the external field. That means they're actually absorbing the energy from the outside, converting it to the internal energy of the system. So that's the meaning of the imaginary part of the dielectric constant. This is the end of the review for this lecture.